we went through the R as part of our computational statistics module. Now we got to a point and we tried to do something. It did not work. I want us to quickly go through it before we continue with today's work. And so if you can start your Jupyter. If you start your Jupyter, let's start our Jupyter. Good. And we might want to bring up what we're working on the other time. I think it was computational statistics. Oh no, computational statistics. Let me see if that's what I have. Yes. Good. So we should start our Jupyter and retrieve the file that we were working on last Thursday. Can you see my Jupyter on your screen? Would like to recreate the data frame. We try to use cbind and rbind, that is row bind and then column bind, and it did not work out. We should have detected why it didn't work out. So let's do it. Let's do it straight away before we go on with today's work. Oh, come on. Okay, so if you have our PowerPoint, our Jupyter on the screen, let's recreate our data point. One moment. Okay, let's recreate our data frame. Let's recreate our data frame. And so let's create names. Should be assigned a vector, with members, Angela, and Chandra. Let's get out of the closing bracket and press enter. Just enter. And then let's do ages. Should be a vector of integers. So let's have integers 27 and 36. Let's jump out of it and do enter. And let's create insurance. Insurance to be a vector of booleans. And so we have 3 lines: names, ages, and insurance. Let's run. I do Shift Enter. There shouldn't be any problem. If there is a problem, just look at the code again. And for a new day, starting with 1, code line 1. Let's put this vectors into a data frame. And let's call it patients. Patients should go into a data frame. Put in their names, ages, insurance. Names, ages, insurance into a data frame. Let's run. When we run, there shouldn't be any problems. If you're having a problem, unmute your mic and talk to me about the problem. And so let's look at what we created as a data frame. Let's run. And so this is the data frame that we created. Don't forget, I said a data frame is in the form of Excel sheet with rows and then columns. Each row talks about a specific case. And so row 1 here, everything has to do with Angela. The name is Angela. Her age, 27. She has insurance. Then you come to Shondra. Age is 36 and she has insurance. When you do the class, you realize that the class is a data frame. We want to use R bind, that is a row bind, in adding another row to Angela. Remember, these things were formed out of vectors. And we said one important thing about a vector. A vector can only contain one data type. A vector can only contain one data type. But here there are 3 data types. Names is a string, ages is numeric, insurance is Boolean. Therefore, we can no longer use a vector. We have to use a list. A list, we said, was a container. And a container can have different types and even what? A list in it. So this was the fact we forgot last time. And then we tried to make it a vector. For which reason? He said no. And so let's create a list. And in the list, we'll put our names. So let's just call it L. Even though L is not a very good name because it does not say what we are going to create. So bear that in mind. And then let's have list and do this. And then names, let's create a name, the same name we created the other time. The same name we created the other time, called Liu G. And then let's have ages, 45. Insurance, oh, come on. Insurance, let's have true. So we created a list. We run. Oh, and not assigned here. And so we have a syntax error. That is it. And so whenever you are doing this business, syntax errors are part of the business. So we want to add this list now to our patient's data frame. All that we have to do is to say we are going to overwrite the previous patients. Then we are going to add it as what? A row. So R bind, row bind. Row bind is a function. And then we bring the data frame for which we want to add the list. And then we add the list. Here, the list is going to be added as a row to the list that we currently have. And then the results will be used to overwrite the patients and store it in what? The patients. So let's do it. And it said, what again? Wow. Huh. I really don't know why this thing is not working for Jupyter. I have no idea why it's not working for Jupyter. You see, I did it in the classical R, and I hope it would have worked for Jupyter by extension. Today too, it did not work, but in classical R, it actually works perfectly. So I have no idea why it's not working. And so we've got to leave it and go on with yes. It works with classical R. I have no idea why it's not really working with Jupyter. And so, well, that is it. Let's maybe I should have checked that it worked with Jupyter before this morning. Let's just go on. Okay, it works when I replace the list by a data frame. Well, let's see. Let's see. Let's see. So let's see if it will work when we replace the list by a data frame. And so I'm going to have here data dot frame. Boom, boom, boom. I run. And then let's see if it will work here. I run. And so this was a suggestion from one of you that she or he, pardon me, I don't know your sex. The participant did the thing by data frame. So we did data frame, whatever we have previously, and then we did R bind, and then it worked fine. Thanks for the education. Thanks so much for the education. And so let me just finish with the dates, and then we go on. Boom, boom, boom. And so we can, now if that works, we can also have, we can add, boom, 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 boom. Yeah. And so if that works, let's spill out to see what we have. I'm not sure about. So the participant who told me it worked, you see, here we have a problem somewhere here.
Yes, Professor.
Yes,
And
sir.
this NA comes from the fact that you compile, you execute before. So normally, if you rerun the code from the beginning, it should not give this NA.
Okay, okay. So if I rerun the code from the beginning, right?
Yeah.
Okay, so let's see. We run, we run, we run. We run, run, run. Let's see. Okay, you are right. You are right. Your name, Toussaint or Toussaint?
Yeah. Toussaint.
It's
I'm
Toussaint.
Toussaint.
That is French, I suppose.
Yeah, it's French.
Okay, thank you so much. And so it should work. It should work now. It should work now. And so in Jupyter, remember, it's data frame to data frame. But in traditional R, all else should actually work. And so let's do column bind. Now, this is a row which we are binding to the previous data frame. Now we want another column. Why are we doing this? It's essential because sometimes when you are dealing with data, that's the way it behaves. So this particular stage, we call it data wrangling. Data wrangling. You want to be able to get the data in a form that you can actually subject to analysis. And so let's see the next appointment dates of our patients. Let's have next appointment. Let's capture it as a vector of dates. So let's capture it as a vector of dates. I'm going to explain the date format. Zero 04 14 then I have 02 25 2016. And so we have 3 dates. But as it stands now, these are not dates. These are strings. So run first. Let's run first. It has run. Let's look at what it is. So let's do type of. And then let's do so do next dot apt. Let's look at it. Next dot apt. It says character. It says character. And so what we created here, that is on line 16, understand that it is character rather than date. You are seeing it as date. R sees it as character. And so we have to convert it to date. There are so many formats of dates that R uses. Some of it is month before the date, before the day, before the year. Some of it is day, month, year, like we use in English West Africa. And so you should know whatever date you are looking for and then look for the appropriate format. And so let's convert. We'll do next dot appointment should be assigned as date. And then we'll pass the date. And then we state the format in which we want it. And so we are converting the character to a date. So we say as date. And the date should be in the format of the month, the day, and then the year. And so we run. When you run, silent, and then let's look at our date to see if yeah, you can see it came out the way I wanted. The year, the month, and then the day. So we would add it as a column bind to here. Here, we'll add it as a column bind to this. Let's add it. We'll do patients. We are going to override patients to be column bind. Then we'll do patients. Let's pray this works. And then we'll add our dates. We'll add our date. We run. We just lucky. Why today? And so let's see patients. That is it. And so now we have names, ages, insurance, and then your next appointment date. There are so many other operations that you might want to subject your data frames to. A full course in R will give you those things. And so I'm going to provide links, and then these links will take you to some of those lessons. And so we tried to do edit of Titanic last time in Jupyter. That also didn't work quite properly. And so I would advise you, it's good to either use RStudio or the good old R. The reason why we are using this Jupyter again is, I emphasize, we don't have enough time for our lesson. It's just a couple of hours. That is why I chose the R. And myself, I've never used R in this environment before, but it's because we have to do it very fast and we want to avoid errors. That is the more reason why we chose to use Jupyter. So my advice is always to keep to plain vanilla R or RStudio. Any questions before we go on? So we looked at program flow. And under that, we spoke about using the if statement, the if-else statement, and then the nested if, and then the multiple versions of it. What we said, we always going to have conditions. These conditions would evaluate into a logical, which is either true or false. True or false, we refer to it as a Boolean in R. And then if the condition evaluates to true, in that case, the if block executes. If it evaluates to false, it jumps out of the if block to see if there is an else. If there is no else, that ends it. If you have just if, but if there is else, it evaluates it. If there is an if, it also going to evaluate the condition there again. So we did that. We looked at logic and relational operators. Relational operators, we said less than, greater than, less than or equal to, greater than or equal to, and not equal to. And the logic operators, we said in the logic operators, we can have and, or. So we did some examples where we said true and false will be false because a statement cannot be both true and false. But true or false is going to be true because a statement can either be true or false. So we did that. We did that. Then we came to loops. I think just about loops that we had to break the class because the woman had to meet the class. Now, can we see the slide on the screen?
Yes, Professor.
Okay, good. So let's start with the for loop. We said when a program is executing, it executes in 3 modes. Sequentially, that is, it executes line 1, and then it goes on to line 2, line 3, line 4, and so on and so forth. Then you can have branch statements. In a branch statement, it executes up to a point, and then it tests a condition. This condition can either be true or false. And so if it's true, it takes a route. If it's false, it takes a route. That is what we call a branched statement. The third mode is something has got to be executed more than once. So when it gets there, it's going to loop through that section of what? Code. Because it's been written that when it gets there, it should execute that section of code X number of times. We call that process iteration. Iteration. And for iteration, we have basically 2 modes. We can have what is called a for loop, And then we can have a while loop. So in the for loop, this is the nature of our code. When it encounters a for statement, what it means is potentially it will be doing some loops. And the for statement has this here. It has a condition there. That value in values. As long as that condition remains true, it executes this action. As long as this condition here remains true, it executes this action. It stops this action if only this condition turns out to be false. And so the for function has a condition, and then the body of the for loop. The condition can either be true or it can either be false. If the condition turns out to be true, the action is executed. If it's false, it jumps out of the action. And so this typically what you write for R. We said for the index I in 1 to n, do something. And so long as the index I is a member of the set 1 to n, it will keep doing something. It stops if only I is no longer a member of the set 1 to n. So an example is this. I can say for, then we have I for I, stop autocorrect. Yeah, in 1 to 5. Yeah. So print. Hello. Good. So look at this snippet of code. Look at this snippet of code. Good. We said, so long as I is a member of the set 1 to 5, print hello. So initially, we are going to take I to be 1. Then we ask ourselves, is 1 a member of 1 to 5? Yes. We'll print hello. Then we'll come back. We'll increment I to 2. Is 2 a member? Yes. We'll come back and print hello. Then we'll come back, we'll do it, we'll do it, we'll do it. then 5 will do it. And then I will now set to 6. Then you ask yourself, is 6 a member? No. If 6 is not a member, it will skip this line, skip this curly brace, and come here if there are other code statements to be executed. In some other languages, in fact, if you've done C++, you see that this is the way they write it, that I equals 1. That's the initial statement. And then this is the critical condition that is being tested. And anytime it's executed, it should increment I by 1. That is the way you have it in C++. In R, it does not exist. And so let's see here. You have for I in the vector, Reto, Ben, Leah. Print I. So it will print Reto, it will print Ben, it will print Leah, and then it's done. When it's done, it jumps out of that particular statement. And so you can have also this names into a vector. The names were made into a vector because of the keyword here, C. And then a vector is stored in participants. And so we come here to say, okay, for name in participants, that is, we are looking for a name in participants. Who are the participants? They are Reto, Ben, Leah. Print name. And so you keep doing that until you print out Leah. And once Leah is printed, it means there are no longer names to be printed. So you have to jump out of the statement. Let's go to our Jupyter. Let's go to our Jupyter. Can we see the Jupyter now? Can you see the Jupyter now?
Yes, Prof. I can see it.
Okay, so let's do it. Participants should be a vector of, let's have Reto. Let's have Ben. Let's have Leah. And I would execute. Then from there, let me see, I have 4, and then I have the function. So let's have name in participants. Ooh. Name in participant. And this time it's curly braces. Curly braces. Let's do enter. And let's see what the code should do. So we have print, and then we say just print name. Let's execute. And so it comes. We are saying if name is in participants, then print it. It printed Reto. Then if name is in participant again, print it. It printed Ben. If name is in participants, yes, printed Leah. If name is in participants, we don't have any name in participant again. And so this is doing something over and over again. There are some other interesting parts of the for loop, which has keywords break and continue. Those ones will be left for you to read so that we can make progress. We can also have reverse loops where whatever you are to loop over, you do it in the reverse directions. Now, R particularly has no such structures to do the reverse loop. We have got to be smart in writing our code in order to achieve that. And so let's take an example. Let's have a function and have x should be assigned 8 to 11. Let's execute. You know, if you didn't bring the brackets, if you didn't bring the brackets, X would have stored 8 to 11 silently. And to get what it is stored, you have to explicitly bring X before it shows these figures. But when you bring the brackets before the statement and you execute, it will bring it to you at once. So let's say you want to reverse the values so that we print 11, 10, 9 before 8. All that you have to do is to bring the word rev, stands for reverse. And then when you do it, it reverses the numbers for you. We can use such a strategy in formulating our for loop to actually print whatever we want in reverse or execute statements in reverse. How are we going to do it? An example is this. Let's do for loop. Let's do for loop. So for I in 3, 1. Let's bring the set of braces. Do enter. Let's do this. And then bring in I. For I in, instead of 1 to 3, we do it 3 to 1. And then we say print I for us. When we execute, this is what we get. And so let's do it for the vector of names that we had. So names in reverse, and then let's layer, and let's have Reto, Ben, Leah. Let's have the pair of braces. I enter, and then I have print name. Execute. Because you've layered reverse over the vector, it's going to print layer Ben before recto. And so this is the trick. If you want to execute code in reverse in R, because R does not explicitly provide for doing things in reverse. There is also the while loop, and it operates on the same principle. Now, let's come to an important point now. Let's come to an important point. We've mentioned previously what are functions. We said a function is nothing more than any mechanism that takes an input, processes this input, and then gives you an output. That is all a function is. And we came across some functions already. Print, we give it something and it prints it for us. Head, when we have a data frame and I want to look at the first few 6 values, we do head. If you want more than that, we do head, the data frame, and let's say 10. The same thing applies to tail edit, which did not work in a Jupyter, but it should work in other R environments. And then round, if we have a value with so many decimal places, we want to round it to let's say 3, 2, 4, or 5 decimal places. All these are functions. We'll come across, well, let's do an important function called getWD. GetWD. The WD there stands for working directory. Working directory. So let's go back to our Jupyter and do getWD function. GetWD function, that is get working directory. Let's execute. When I execute it, I get C, user, users, user. You should get a different thing. Perhaps you should get C, users, and then a name of your laptop. Is that not the case? Florence, what did you get? No, it's not Florence. It's Florentia. Florentia, what did you get?
I get users Flor Tames.
Okay.
That's my laptop's name.
Exactly. Exactly. And so when you start your Jupyter, or indeed your R or Python, you have a default working directory. And working directory here means a folder. You have a default folder. This is where your R is pointing to right now. Everything that you are doing, R is saving it in that particular folder. We are going to be changing this folder very, very shortly, because when you are doing a project, you collect the data, you don't save it in the C users, let's say Florentia. You might save it in a particular folder, and then you might want R to be pointing to that folder so that you can read the data and make use of it. And so all these things are functions. Another function is what you call round. And round passed with pi. When you execute, you are going to see that pi comes with so many decimal places. That is the pi in mathematics. We want to have pi to 2 decimal places. When I execute, I get this 3.14. If I just do pi, this is what I get. And so for 2 decimal places, it will just cut it at 3.14. And so when we talk about functions, we have built-in functions, and then we have user-defined functions. With built-in functions, these are functions that come with R. So those that we've been using, for example, head, tail, round, getWD, these are built-in functions. But the work we are going to be doing, sometimes the built-in functions are not enough. We are going to be building our own functions. And building our own functions, we call them user-defined functions. And so, once again, a function is just a self-contained module of code. This is the plan for our function. Every function has a name. Every function has a name. And then you define the function itself. So you have the word function. And then here you have ARGS. ARGS is for arguments. That is the input that your function needs. Functions need, well, most functions need inputs. So the inputs are passed to the function here. They have the body of the function. That is a pair of braces. A pair of braces. Then what you want the function to do. That is going to be expressed in statements. After the function does those jobs, what should it return to you? You bring the keyword return, and then whatever we are expecting from the function. That's the way all functions are. And indeed, if you want to write our own function, we just follow this format. It's straightforward. And so to add maybe 3 to something, we just give it a name. Let's say add 3. Add underscore 3, which is like a variable. All that you need to do is for the function name here to communicate what the function is going to be doing. Once again. Are you there?
Good morning, sir. We are here.
Yes. Yeah. My apologies again. Stuff happens. The internet went off. I had to go down to check, and we restored it now. So we can go on now. Any questions so far? Right. So We're talking about creating our own functions. I'm panting a bit. We're talking about creating our own functions. And we said we have to give our function a name. And the name must reflect what the function is going to do. And then we bring our assignment statement, the keyword function, the inputs. Here we call it argument. The pair of curly brackets or the braces. And then what the function should do. In this case, we are saying when we give you an input, let's say 7, add 3 to 7 to get 10. Store the value of 10 in output and then give us the output. That is all. And so this is an example of a function. We want to call this function adder. Adder, that's to add numbers. And so the function name must always reflect what the function is going to be doing. So adder is assigned then a keyword function. The inputs, 2 numbers. And then we have an opening brace, a closing brace. What should the function do? The function should just add these 2 numbers and return the results to us. So return into bracket m plus n. That's all. Let's go back to our Jupyter. Let's go back to our Jupyter. Let's go to our Jupyter. Screen, that should be it. Can we see the Jupyter on the screen?
No, sir.
Not yet.
Man, I struggle with this and eventually. Maybe we can see it now.
Yes.
Yes, sir.
Okay. So let's write a function called adder. And give it 2 arguments, m and n. And let's have our braces. Do enter. So the outline should look like this. Adder is being assigned a function which takes inputs m and n. And then we have the pair of braces. And so this is the outline. And all we want is if I give you two numbers, just add them for me. That's all. And so return to me. And then I have a pair of brackets, M space N. That is my function. Let's run. And so we formed this function to take two values, M and N, add the results, return the results to me. Anytime we need this function, we have to call the function. To call the function, we call it by the function name, which is adder. And then supply it with two values. And so let's call the function adder. And when we say function, we should always have the pair of brackets in front of it. What do we want? We want it to take two values. Let's say 7 and 32. Let's run. It gives us 39. And so on line 31, we wrote our function. And when we wrote our function, we said to take values M and N, add these values, return the result to us. It's on line 31 that we are actually defining our function. On line 32, we call our function. 7 goes in place of M. 32 goes in place of N. And then the result is 39. This is the architecture in which all functions that you find in R are actually written. And so we are going to experiment with writing a function to solve the quadratic equation. The quadratic equation, let's see if we can see the slide on the screen. Can we see the slide? Yes. Can we see the slide?
Yes.
Okay. So the quadratic equation says ax squared plus bx plus c equals 0. That is, we want a value of x, which you will substitute in this equation for it to be 0. An example could be x squared minus 5x plus 4 equals 0. That is an example of a quadratic equation, actually. And so I'm going to call the function roots. Roots. To reflect the fact that whatever solution I get for the quadratic equation, we call these solutions the roots of the quadratic equation. And what should we take? It should take the values a, b, oh, b, and then c. That is the constants a, b, c. That is it. It's taking it here. Now, if you remember from high school math, there is something you call the discriminant. And the discriminant is b squared minus 4ac. That is the stuff that you have under the square root. If you don't recall immediately, let me just remind ourselves. The roots are given by x1, x2 will be assigned, yes, we have negative b plus or minus square root of b squared minus 4ac over 2a. This yeah, so this is the equation. This is what we used to solve quadratic equations in high school. x1, x2 will be negative of b plus or minus the square root of b squared minus 4ac, all divided by 2a. This value here is what you call the discriminant. We call the value the discriminant. It's called the discriminant. The discriminant. Why is it called the discriminant? Discriminant comes from the word discriminate. It discriminates the equations, no, the roots that you can have. When this value equals to 0, when this value equals to 0, the equations that you have are equal. That is, if it's equal to 0, square root of 0 is 0. And so what you are going to be left with is negative b over 2a. Therefore, x1 equals negative b over 2a. x2 equals negative b over 2a. When this value here is real, and if I say real, let's say the value under the square root is 16. Square root of 16 is 4. And so that is what? A real number. In that case, you have what you call real roots. Suppose this value here is negative. It's negative. Of course, you have experience using calculators. And for some type of calculators, if you want to find the square root of a negative number, it tells you error. Well, it's not error. The square root of a negative number is what you call a complex number. And so if the discriminant is a negative number, the square root therefore will be a complex number. And so the roots will be complex roots. That's all. And so let's come here. In your function, you are going to find the discriminant. And then if this discriminant, whatever you find, you store it in D. And then you test. If D equals 0, that means the equation has what? Equal roots. Else, if D is a positive number, then it has real roots. Otherwise, that is, if it's a negative number, then you have complex roots. That's all. And so let's write this function. Let's write this function. Let's write a function. Let's call it roots, and that should be assigned a function. Then let's have A, B, A, B, C. Let's have this. That is the outline of the function. The outline of the function. And then let's define the discriminant to be b squared minus 4ac, 4 times a times c. The first thing to look for is the discriminant. Then we are going to test the discriminant. We'll say if, then we'll bring this. If the discriminant equals 0, remember, we said 2 of the sign means equals. Let's bring our pair of braces. And then let's have this. Let's print a statement to say we have equal roots. Let's jump, and here let's write else if. Then let's have, if the discriminant is positive, that is greater than 0, let's jump out the brace and say print. We have real roots. Let's bring else. And say print. We have complex roots. And so we've written the outline of the function to solve quadratic equations. And so let's run. Did the equation run?
Yes.
Okay. Thank you. And so let's try it on an equation like this. Let's suppose we have an equation. Let's suppose we have an equation. Suppose we have an equation x squared minus 5x plus 4 equals 0. Boom, boom, boom. Okay, so let's say we have an equation x squared minus 5x plus 4 equals 0. We want to know the nature of the solutions, whether we are going to get real solutions, we are going to get complex solutions, or we are going to get equal solutions. And so in this equation, A equals 1, B equals -5, and C equals +4. We'll call the function and substitute these values for A, B, and C. And so let's go back to our Jupyter. The function's name is roots. And A is 1, B is -5, C is +4. Let's run. It says we have real roots. That means if we evaluate b squared minus 4ac, the value that we get is going to be positive. And if it is positive, then this portion evaluates, which says we have real roots. Let's try another equation and see. This time, let's have this. Let's have x squared plus 5x plus 4, meaning a is 1, b is 5, c is 4. Let's substitute into roots and see what we get. We do roots into bracket 1, 5, 4. Let's execute. Does it say we have real roots? I'm wondering. I'm wondering if you have real roots. What is b squared is 25 minus, yeah. Let's try some other one. Let's try this. That is 1, negative 1, 1. An equation like this. Let me grab you. Let me grab you. Good. Let's try an equation like this. 1, negative 1, 1. Let's try an equation like this, which is x squared minus x plus 1. X squared minus x plus 1. So we have roots. Then we have 1, negative 1, and then 1. Let's see. We have complex roots. And so this is just the outline of the equation. This is just the outline of the equation, which tells us the nature of the roots. Your responsibility will be, now, if you know the nature of the roots, write into this to find the roots. You should attempt it. You should attempt it. Yeah, you should attempt it. Yep. Let's do the slides before we take a brief break. And so, what is the nature of data that we use in R for analysis? Some of the data we are going to store is in what we call CSV. That is comma separated values. Comma separated values. It also has another name, I've forgotten. Is actually stored in Excel. And then in Excel, we go to say, okay, give it a comma separated value. Or we can store data in just plain text, notepad, or in Excel. That is XLS or XLSX. We can also import data from SPSS, SAS, and actually Stata. We can go to websites to see if data is there. And then once we write the name of the URL, we can import that data into our R. Then, of course, we can import data from databases using what is called SQL. The storage of data for purposes of long-term use is done in a database. Stable. Built-in data comes with the installation of R. R comes with what you call packages. And we are going to be using some of these packages. All these packages probably comes with data for use in learning. And so if you want to know the data that R comes with, we type data as a function. Let's type data as a function. So I said this function, we've just written it in outline. You should complete it so that whenever I put in any quadratic listing, it should just spit out the solution for me. Let's type data and run. Okay, so when you type data and run, it gives you some of the inbuilt data that you have in R. What I have perhaps will be different from what you have, because I've been using R for so long. So scroll and you have some of the data. Do you all have this?
Yes.
Okay, so this is just for learning. This is just for learning. If you want to learn R, you can just call on each of this and then you use it to learn. And so it's 11 now. Let's take a 20-minute break for us to have coffee. Let's come back. Air passengers is one of the data files that you can have that you can use in learning. we are concerned with our own data that we want to use in our analysis. And so when we collect or download data from other official sites, this data can be in the form of comma-separated values or tab delimited file. If I say comma-separated values, I'm talking about so most participants would know what you call comma-separated values, isn't it? So that I don't have to bother myself to go to that. And then tab delimited values are normally stored in Notepad. So R can read files in the following formats: CSV, TSV, delimited, fixed width files, tables, and so on and so forth. Look, all that you are going to be using realistically for your research are TSV files and XLS files. If there is a file which is in SPSS or SAS or those things, it's just straightforward reading them directly into R. And so I sent out some data. And that data, I said you should create a folder on drive C. And that folder, you should call it Computational Stats. That is Comp Stats. And then drop the data, which is insurance.csv, into that folder. Did we get that small process right? The question again, did we get the process of creating the folder named Comp Stats onto the
Yes, we
C
did.
drive? Okay, thank you. So we said earlier on that if you start any of these languages, it points to a default folder that is the same as the name of your computer. Normally, that is not where your data that you use is. Your data that you use is going to be in a folder that carries the name of the project for which you collected the data. Let's say you collected malaria data from West Africa. You are going to have a folder to say West Africa malaria. That is where you put your data. And so you've got to redirect R from the name of your computer to the name of that particular folder. That is what we want to do now. And so we saw that if you do get working directory, and then you run, it should point to where R is looking at presently. That's the default folder. And now we want to change to the folder that we created. To do that, use the function set WD. That is set working directory. And under set working directory, it's going to be a string. So you bring this. And then the path is going to be C:// and then you bring computational statistics. Comp stats. Run. If you run, it should take you to the folder that you call comp stats. Did it work for all of us?
Yes, it's work.
Okay. What about the rest?
Yes, it worked.
Okay. And so this really is simple. You know, you have folders in which you have your various projects. And so if you need a particular project, you just do set WD and then quote and then the path of the folder. I don't have this folder, but I have a folder called Python projects. And so you are in C computational statistics. I am in C Python projects. In your folder, you have data, and that data says insurance.csv. So let's see if that data is there. Let's see if that data is there. And so you type directory, and function. So run. When you run, you should see insurance. Now I have lots of stuff in the folder. So I should have insurance here. If I don't have it, that'll be serious. Huh. IJKL insurance. Wow. I can't see insurance anyway. Well, okay, so let's read the insurance data. Let's read the insurance data. Let's just call it data frame. To be assigned. So what we do, we read it with read.csv. This. And then we do this. And then you do insurance.csv. And so let's read the insurance data. I run. Have we run the code on line 41 successfully?
Yes.
Yes, sir.
Okay. Okay. And so let's take a look at the top values. I'll do head and do into bracket DF. When I do it, this is what I have. Yep. This is what I have. You know, health, well, insurance companies spend a lot of money in paying out medical insurance. Now, in order for them not to make losses, they collect this data and then they model the data so that next time you are coming for insurance, they ask of your age, your sex, they take your BMI, number of children that you are coming with, whether you smoke or not. This insurance data was from US. So whether you are from Southeast, Northwest, North, or something, and then the total amount we paid on you. They collect all this historical data, and then they use it to build a model. So that next time somebody is coming, we are going to input these values: age, sex, BMI, children, whether the person is a smoker, the region, and then we'll know how much we are going to be paying potentially. So this is what we are going to do. We are going to use this data to build a model. And then when you are coming for health insurance, we'll input the values to know how much we'll be paying on you potentially. And then based on that, we'll charge our premium that you are going to be paying per month or per year. And so let's take a look at the tail end of our data. But now let's look only at 3 observations. Let's run. Now, there is, and so this one, you can only look at the top and then the bottom. You cannot randomly look at values. To randomly look at values, you have to install a package we call psych. And based on what you do, psych is going to be one of the packages that you are going to be using every day, every single day. And so straight up, let's learn how to install packages. You see, R is a statistical package, and you use statistics in almost every field in life. But depending on what you use statistics for, there are various packages. And so I believe in medicine, in epidemiology, and so on and so forth, there are packages even called EPI that you use in doing some of the things that you do. There are packages that does survival data, fertility, regression, and so on and so forth. And so all that you need is to pick an R book specifically on what you do. And that book is going to tell you the packages that you need for your work. And so let me use the opportunity to show you how to install packages. We want to install a package called psych. So you do install.packages. And then you bring the function. And then the package you want to install is called psych. Now, the package that you would install depends on other packages. And so if it depends on other packages, you remember to tell R that the package I'm going to install, which is psych, will depend on other packages. And so you do dependencies. And then you do true. That is how you install a package. And then let's run. Yeah, it's working. So when you see the asterisk here, it means the process is taking place. If you have done it on R or RStudio, when you do this instruction, you see all the dependencies that are going to be installed. They'll be coming up and then disappearing. They'll be coming up and then disappearing for you. And so whilst this is going on, we can go ahead with the rest of our lesson. Yeah, so that tells you the dependencies. And so the psych depends on all these packages. Lavan, again, what you do, I will urge you to learn a package that we call Lavan. Lavan is used for what you call SEM, structural equation modeling. Structural equation modeling. Yeah. And so let's do what is called exploratory data analysis. Whenever we have data and then we want to analyze, we do exploratory data analysis. In exploratory data analysis, we want to know the data in general. We want to know how the various variables in the data are related to each other. We again want to know if there are any extraordinary stuff in our data. Is it linear? Is it non-linear? Do we have some extremities? That is all that we look for in our exploratory data analysis. So first off, let's look at the names of our variables in the data frame. So we'll do names and then we'll do DF. When we run, ooh, because it is doing this installation, to finish this installation before it does this. Has anyone's installation been able to complete? In fact, I didn't have to install this. I didn't have to install it because I already have it. Yeah. And so I interrupted it. Hopefully it should stop. Has yours finished installing?
Yes,
Sorry,
mine
no problem.
finished.
Sorry, mine is
Okay.
saying dependency lattice is not available. Also installing the dependencies.
Okay. So what are you using? Are you using the Jupyter, or you are using Jupyter?
I'm using Jupyter Notebook.
You are using the Jupyter Notebook.
Yes, bro.
I would advise that whenever you want to do these installations, install it through plain vanilla R. Yeah, it's much less stressful. Look. I shouldn't have installed it because I've already got it. It will just delay us. Okay, so don't worry. I'm just going to start a new I'm just going to start a new Jupyter. And so I go to set WD. Don't do this. I'm starting a new Jupyter so that so let's have Python projects. I'll do this. And so I have DF being assigned read.csv. And then I have insurance CSV. Good. And I have a head. Come on. I run. Yeah, that is it. So can you see my Jupyter now?
Yes.
Okay, good. We are back to business. Whilst that takes its time to run through. Yeah. And so I told you what we do in exploratory data analysis. And in exploratory data analysis, one of the things you do is visualization. You want to know your data. There are qualities of visualization. Those qualities are on your slide for you to read through so that we don't waste time. But suffice it to say, we want the visualizations to be truthful functional, beautiful, insightful, and enlightening. So I sent another data set called code.csv. And so let's read that particular data. Let's read that particular data. No, download both files. That is code.csv. Don't change the name of the file. Just download it as it is into the computational statistics folder. Right, I believe most of us have been able to do that. And so let's do code is assigned read.csv into bracket, into quotes. Let's read the CSV. Now you are going to see that most of the work that you are going to be doing, the data is always in the format .csv, because this indeed is the era of big data. Data files that you are going to be getting are always very large. And the CSV extension optimizes the size of the data compared with Excel. And so if you have data, you are advised to convert it to a CSV file. And so let's read. None should be lag behind. Have we been able to read the code data?
Yes, sir.
Okay, good. And so we've read the code data. Let's look at the size of the data. We'll do dimension, and then we'll pass code. And that is it. It's relatively small data. It's made up of 1,254 rows and then 10 columns. Let's look at the variables. So we'll do names and then code, run. And so the variables are intensity, prevalence, area, year, depth, weight, length, sex, stage, age. And so take a look at the head and at the tail. Take a look at the head and then the tail of the data. That exercise is always necessary for you to have an idea as to what you have. I think it was health data, but I can't remember exactly what the area it came from. And so here we are going to do a bit of what you call data wrangling. Data wrangling. When you look at the data, you are going to see zeros, ones, and so on and so forth. Some of these zeros are logical. That is either true or false. And one moment. Oh. Someone cannot hear me. Yes, my audio is on. The video is also on. Oh, this is just me. I cannot hear anything. Wow. Yeah, my audio is on.
Yes, Professor, we can hear you. Thank you.
Okay. So if you can't hear, just take off your earpiece and put it back in. You should be able to hear. Okay. So some of the variables, we've got to convert them to actually what they are. So prevalence is a logic. It's either true or false. Let's make it to be true or false. And so let's write code this $sign. We came across it. We said it's one of the ways of assessing members of a data frame. And so prevalence should be assigned as logical. And then into bracket, we have called that prevalence. And so we want to convert the prevalence here, which is 0, 1, 0, 1, 0, 1. No, we want to convert it to whatever it should be, which is true or false. And so we do code, and then we call prevalence. We make it as logical. And then we use it to overwrite whatever you had there previously. The overwriting, you are going to be coming across it a lot. It is to prevent variables from just hanging around. And so let's run. When we run, let's see what we've done. Let's just bring four values. That is it. And so prevalence now, where you have 0, it said false. And where you have 1s, it's going to say true. So let's say till, let's bring code. Let's say 10 values. Till code 10 values. You see, so whatever you have once in the data, it changes it to true. Then one thing we have is the area. Look at the area. Look at the area. We want this area to be a factor. And I believe in your work, you came across what is called a factor. A factor is a nominal value. Nominal value, we came across it the very first day. We said it's just a label. So we can have male, female. Yes or no. These are what you call factors. The same way areas, area where we make an observation, we want to regard them as factors. And so we have to convert it to a factor. We do chord, and then we do area. That should be as a factor. You do this, and then you do area. That has been converted to a factor. You run. And then you do head, chord. Let me just look at 3 of them. That is it. So area now is now a factor, but not just a string. If you do type of chord and then area, it should tell you is an integer now, because R uses integers to represent factors. So it's going to be, this might be 1, and then another type 2, another type 3, another type 4, and so on. Then for sex, it says 0 and some other thing, maybe 1 or maybe 2. Look, we want to represent it by male or female, male or female. So we'll do chord, and then we'll call sex, and then we'll do what we call cat. And then in the cat, we have chord, and then sex. And then we want just 2 labels for sex, that is male or female. So we'll put here 2. And then we'll do labels to be a vector of male and female, I believe, yes. Yeah. Called $sex, because we want to override whatever we have previously. And then to do it, you bring the function cat. And then we are rewriting sex, which is 0, 1, 0, 1, just 2 levels. and the levels, we want to name them male, female. So we run. And when we do that, let's have a look at it. We run, that is it. See, previously it was 0, 0, 0, 0. Now we said 0 should represent male, and then female should represent 1. There are some values that are missing in this data. You see, if edit had worked in a, no, let's check why edit is not working in a, why edit is not working for Jupyter. Let's find a solution. Let's find a solution. Let's all use the internet to search for the solution. Edit. Not working in Jupyter for R. Has anyone got something that is close? And so edit function not working. Okay. Anyone close to the solution? This change. Eno, Etel, Ambo. Whew. Well, okay. So editing package is not taking effect in Jupyter. No, that's not what I'm looking for. Okay, so let's just look for the solution. I believe it has to exist. So we might want to test to see if there are any missing values in our data set. There are any missing values in our data set. We do is.na, and then we pass to it code, I believe. Yes, let's run and see. This is not informative enough because it will be difficult for us to yeah, it's actually difficult for us to see. And so when we see through in any of this, that means forget about it. But there are some missing data here. And so we have to omit those missing data points. And so you do code being assigned. Missing data is NA, not available. NA, not available. And you omit all the non-available data from, okay. So first. Let's do dimension of code. Let's run. Dimension of code. Let's run. Our data set has 1,254 rows, 10 columns. Now let's do code is assigned. Let's omit all the non-available in code. Let's run. Let's run. And then let's look at the dimension again. Yeah, so you can see. You can see from 1254 to 1191. And so we had loads of not available scattered throughout our data. This is the process of cleaning the data. Whenever you have data and you want to get the data in a form that you can really analyze, these are some of the steps that you take. And so having done that, we want to look at, we've cleaned the data. Let's come to the EDA now. In the EDA, we are going to take our response to be the fish weight and length. You know, our data to be the fish weight and length. And then this is a lot. This is a lot. Okay, so let's quickly run over this. Let's quickly run over this. Let's look at weight. Let's look at weight. And so names again, code. Let's run, and then we are going to take weight. We are going to take weight. Let's do a summary of weight. That is code of weight. Code of weight. Now, if you take the weight values, the minimum weight in our data is 34. Maximum 9,990. Now, if you arrange the weight in increasing order, a quarter of the values will be less than 969. No, 769. A quarter of the values. This is what we call the first quartile. A quarter of the values will be less than 769. Then the median is 1,446. The median is also what you call the second quartile. Then the mean, if you add all the weights divided by the number that we added, we'll have the mean. Then the third quartile, 3/4 of the weight will be less than 2,232, or a quarter of the weight will be greater than 2,232. This all exploratory. And then we want to know the standard deviation and then the variance of our values, the weight values. So we type variance that should be assigned variance, and then we do chord, and then we do weight. We jump out, we want to know the standard deviation. So we do standard, let me just make it standard deviation. That should be assigned STD, standard deviation, and then into bracket, chord, and then weight. And so by standard deviation, we are asking how far are the other weights from the mean. The square of the standard deviation gives you what you call the variance. Could not find STD. It's just called SD, standard deviation. So here is it. And so there are other numerical values that you can use for standard deviation. Please, let me skip them. You'll find time to go through it. And yeah, you can draw the histogram, the box plot, and so on and so forth. So the work that we really want to do is basic statistical concepts too. Is straightforward. We've come across lots of them. These types of variables you can read and understand. So we'll skip it. What we really want to do is yeah, linear regression models. Linear regression models, and then we close the class. In linear regression models, we want to know the relationship between or amongst variables. For example, in our insurance data, we want to know how much we spend on you in the form of charges, given your age, your sex, whether you smoke or not, the number of children that you have, and the area that you come from. And so we want to know the relationship between the amount of money spent on you medically for a year, and then all these factors. That process, we use what you call regression models. And regression models, we can have simple regression models, multiple regression models, and multivariate regression models. In a simple regression model, we just look at the relationship between two variables. These variables will be, one, the expenses, whether the expense on you is a function of whether you smoke or not, and other factors. This is an example of a simple regression model. We want to know whether smoking is the main driver of expenses on you. But we know that smoking alone will not be the only factor that contributes to ill health for which we pay money on you. But in this equation, these other factors, we are silent on them because we don't know them. This is called a simple linear regression. A simple linear regression. Some other equation might be, we want to know the wage that you earn. And the wage that you earn, all things being equal, should be a function of the amount of education that you have, the experience that you have, and other factors. So the wage that your employer pays you is driven by the education that you have, your qualifications, and then your experience and other factors. The sales that a shopping mall makes per week is a function of the adverts it runs on television, radio, in newspapers, on social media, and other factors. Someone might walk into your shop, not because the person has seen an advert, but because somebody recommended you. That is an example of other factors. And here, there is a single response. This is what you call the response, or the endogenous variable. And the response is being driven by whether the company has advertisements on television, on radio, newspapers, social media, and so on and so forth. This is an example of what you call a multiple linear regression. These factors here, we call them the exogenous variables, or the predictors. So the predictors are needed to predict a response Then you can also have what is called a multivariate regression variable. And the multivariate is an example of what is known as the structural equation modeling. When you look at the slide on your screen, it says constructive thinking, this functional thinking. Well, constructive and dysfunctional will lead to subjective well-being. These two factors will at the same time lead to job satisfaction. So in this model, these two exogenous variables give rise to two endogenous variables. And so in terms of linear regression, we have two factors leading to one, and then two factors again leading to another. Therefore, you have two outcomes. In that case, this becomes a multivariate model. In our exercise, we are going to look at just a multiple linear regression. The rest, I'm afraid, you have to get a textbook. And so these things we've mentioned, simple, multivariate, and multiple, they are models. Models are built on assumptions. The assumption of our linear models are that the relationship between both the response and then the predictors is linear. That's why we call it a linear regression model. And then the errors are normally distributed. The errors are what I've written here as other factors. An error in data analysis does not mean a mistake. No, it's just a technical term. And so when we take the errors and then we plot, we should get a normal distribution. And then the errors are also said to be homoscedastic. That is, the variance or the standard deviation of the errors should be the same. And then the fourth one is that there is independence of the predictors. That is the predictors: television, radio, newspaper, and social media. These values here should be independent of each other. In other words, radio advert should not predict television, and television should not predict radio. Radio should rather predict sales. TV should predict sales. Newspaper should predict sales. And similarly, social media should predict sales. This last assumption is a problem. Real data, sometimes you find relationships between the predictors in real data. If we generated the data theoretically, would have said, okay, you are independent, but in data that we collect in real life, we are going to see some form of dependency on these predictors. But the dependency should not be too tight. They shouldn't be too coupled. And so we use a value called the variance inflation factor to measure the degree of dependency. We have a cut point of 5, that if the variance inflation factor is less than 5, then the assumption that they are independent holds. If it's greater than 5, we start to worry that they are becoming too coupled. In fact, if it is greater than 10, then we know they are too coupled to be used in building our regression model. In that case, we can either drop some of the predictors, or if that is not possible, we move to what you call regularization models. Regularization models include what is called ridge regression. You can also have something we call lasso, or a combination of ridge and lasso, known as the elastic net. Most of the research you are going to be undertaking, this fourth assumption is going to fail you. Bear that in mind. Bear that in mind. The fourth assumption is going to fail. And when it fails, look at your predators carefully. See which one is predating the other. Make a decision to drop that. But sometimes the theory that you are using requires that both variables stay in your equation. In that case, your conclusion is that linear regression model is just not the model that you need in that analysis. And so you move to regularization. You try ridge, you try lasso. The best mode is what you call elastic net. So let's bear this in mind. And so the regression model is given by this, as you can see on the slide. That is your regression model. And what you seek to do is to find this betas, beta naught, beta 1, beta 2, up to beta p. That is all that we seek to do in a linear regression. There are so many methods of finding the betas. One of the popular methods is called OLS, that is ordinary least squares. In ordinary least squares, you try to minimize the errors between the observed and then the predicted values. And so this is some small bit of math that you actually use. Take your time and sit through this. It's straightforward. And then we also have what is called method of I'm trying to rush through this, so I'm sort of getting confusion. Is MLE, maximum list, well, MLE. So we have OLS, we have MLE that we use. Normally, OLS is the most popular method. And so let's come back to our medical insurance data and model the data. We've been able to assess the data already, and then we stored it in DF. I'll read the data and then we'll work with it. So this is not code, it's marked down. Now allow me to read the data. You have it, so you don't have to do this. So read .csv, and then we have insurance .csv, and we do string as factors. No, let's just read it as, okay. String as factors. True. Let's read the data again. Let's read the data again. Let's read the data again. So let's type this code. We are reading this data. And then where it has strings, let's regard the strings as factors. It's essential. It's essential. So let's read the data again. Did you see or you did not see strings as factors? Strings as factors. Yeah. Let's read the data again. Data frame is assigned read.csv, the data. Then whenever it sees a string, it should regard the string as a factor. We are going to be out very, very soon. Just bear with me. So having done that, let's take a look at the data. Yeah. Have we been able to get this?
Sir.
Okay. And so what we are seeing is, you see, whenever it sees this or this, it should regard it as what? A factor. Otherwise, you saw what we did for pod. We have to come and change this to a factor, and then we have to come and change this also to a factor. One of the things we can do is to bring an argument which says strings as factors, true, and then it does it for us. Yes, and then till we'll have it. And so we'll just do this. Let's look at the nature of the data that we have imported. Okay, good. So let's do string our data. It tells us we have a data frame. We have 1338 observations. That's the rows. And then 7 variables. It says age is an integer. Sex is a factor because we said it should make it a factor. BMI is a number. Children, an integer. Smoke is a factor. Region is a factor. Charges is a number. So I'll skip this portion and then you do it. Let's go straight and look at, I'll skip here too, where you do the correlation among the data. And here too. So I'm here. We want to fit the linear regression model. We want to fit the linear regression model. And so let's just give it a name, fit. When we bring LM, it means we are fitting a linear model. And then we bring this. So we'll write our equation now. We'll write the equation now. Now, if you look at our data, the values, age, sex, BMI, number of children, smoking, these are low values. And then the charges are very, very high values. In data analysis, what you do is you moderate a very high value to have similar values as your other values. And so you take the log of charges. You see, it's in the tens of thousands. Here's just 19. Here's just 27. So you moderate these values by taking the log of these values. And so we'll come here and do log of charges. And then from there, we'll do tilde dot comma data, and then we say df. What tilde dot means is you are saying charges should be regressed on the rest of the variables that you have in the data set. That data set is the DF that you imported. And so the log of the charges will be regressed on region, smoker, the number of children that you have, the BMI, the sex, and then the age. And so you run. When you run, the equation runs, and then the results are stored in FIT. To see those results, you just do summary. You do this, and then you do FIT. Yeah, you have 7 minutes more. And then you run summary FIT. When you run summary FIT, you see, this was the equation that you built. These are the residuals. And the residuals are the errors, the other things that you did not include in your equation. This is now the output from your equation. These estimates here are your beta values. Remember, we said all that we have to do in the equation is to find our betas. And we have beta naught, beta 1, beta 2, and so on and so forth. And so the intercept is your beta naught. The intercept is your beta naught. Age is beta 1 associated with age. Here you find something strange. You say sex male. It did not bring sex female. And this is what happens. Whenever you have factors, it's going to hold one of the factors as a reference. And so it held sex female as a reference. And so sex male is going to be interpreted with respect to sex female. And then BMI, children. And so these are the betas. But the betas are point values. They are point values. Whenever you have a point value, there is always uncertainty around your point value. That uncertainty is expressed by what you call the standard error. So remember again, the betas are point values. They are single values. Single values in statistics always have uncertainty around them. This uncertainty is expressed by the standard error. The estimate divided by the standard error gives you your t value. The data came from a sample. And for samples, we use t values. The t value, we take the absolute value, that is the value without the sign, to know whether the estimate is different from 0. And so this, the region that is northwest relative to north the absolute value is less than 2. Whatever the absolute value of your t is less than 2, it means the corresponding value here is 0 or insignificant. And so the beta naught is significant. The same thing applied to the beta associated with the age, the beta associated with the male. The only beta that is insignificant is the beta associated with northward, west. These values are what you call the p-values. You've been doing research, you should be used to what you call the p-values. And suppose we choose a level of significance of 0.05. Whenever the p-value is less than 0.05, we have a significant finding. And so you see here, this value clearly is less than 0.05. And so this value is significant. Of course, what the t values communicate should be the same thing as the p values. We said this value here is insignificant. Indeed, come here. You see, it's 0.067. This value is greater than 0.05. And so it is insignificant. And then you come to your multiple R square. This is what you call the R square value, or the coefficient of determination. In other words, we have 76.79% of our explained value in the model. Or you have adjusted R square here, which says 76.66% of the variance of our model is explained by these factors. Then you have F statistic. F statistic is just saying the model that we've built with these factors, is the model correct? Yes, indeed. The p-value of the model is less than 0.05. Therefore, we've built a correct model. 1 o'clock exactly. I have to bring this class to a close. I thank you all for signing up to this class. We hope we would be getting a grant in the future, and would do it in-house instead of online. And so when you hear we are doing it in-house at the University of Cape Coast, apply, come, spend time at the University of Cape Coast, enjoy our university. Our university is the only university in the world that is by the seashore. And so thanks once again for signing up to the program. If there are no questions, we'll call it a day.